All right, in 5.2, 5.1 we explored kind of how they interact with each other a little bit. 5.2 is going to be dealing more with graphing polynomials, which is really cool. I really enjoy this part. So something to note about polynomial functions. They have smooth curves. So here is a polynomial function. Notice there's no like absolute value type things. It's smooth all the way. It does a nice rounded curve. Sometimes it'll look like it goes up super sharp, but it still has a curve at the top, and then it may go down super sharp. But there's no like jagged edges or anything like that. Polynomials have smooth curves. The end behavior can be determined by the degree of the polynomial and its leading coefficient if it's positive or negative. We'll talk about that when we get over here. All right, the end behavior describes which direction it goes on the left-hand and right-hand side. So based on the highest exponent and whether the coefficient is positive or negative, we can determine what it's doing at the ends of the graphs. That's what the end behavior is talking about. We'll get to that in just a minute as well. First thing I'm going to talk about is just like evaluating. So we've done this before. We've done this in Algebra 1, geometry. So just don't forget that evaluating, it just means take this x value and find the y value associated. So if I want to know what y is when x is 4, I can say f of 4 equals 2 times 4 to the 4th plus 3 times 4 minus 2. So now I have 2 times, let's see, 4 to the 4th. I'm going to cheat and use a calculator just to make sure I don't get it wrong. It is 256. And then I have plus 12 minus 2. 2 times 256 is 512. 12 minus 2 is plus 10. So this should be 522. So that means f of 4 equals 522. What that also tells us is that when x is 4, the y value is 522. So this is like way up there, right? This other part, when x is negative 3. Same idea, it's just now x is negative 3. So I'll do 2 times negative 3 to the 4th. Oh no, I'm already running around out of room. Negative 3 minus 2. So now that is 2 times 3 to the 4th is 81. Minus 9 minus 2. So I have 162 minus 11, which would be 151. So f of negative 3 would be 151, which is 3 triple 19s for all you dark numbers. All right. So same idea on part B. Pause the video, give it a shot, see what you guys come up with. I don't know why I'm talking super quiet today. I just realized that. I guess I'm just tired. It's been a long day. You guys are almost done with the first half, so that's pretty exciting. 64 plus 4 times 16. Hey, I got that 64 plus 7. So that should be 128, 135. And then the other part over here, negative 3 to the 3rd, 4 times negative 3 squared, plus 7. So that is negative 27. That is 9 times 4 is plus 36 plus 7. So let's see, that makes 9 plus 7 is 16t. All right, hopefully you got that. Okay. So for the next one, at what values of x does f of x equal 0? Remember, f of x just is the y value. So where does the y value equal 0? Pretty much gives it to you. So I have x equals 1, negative 1, I'm sorry. Negative 1, I have x equals 2, and I have x equals 4. Don't forget these can also be called the x-intercepts, the roots, the solutions, or the zeros. Yeah, the zeros. All right, and then it says, what are the coordinates of the relative minimum and maximum? So relative, all that means is like relative to the things directly around it. So as I follow my function goes down forever and it goes up forever. Apex is bad about arrows sometimes, but it goes up forever in this direction, goes down forever in this direction. So like there's something else called the absolute maximum and absolute minimum. The absolute maximum is the very, 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 very highest point. But since it goes up forever, past our viewing level, there is no absolute maximum. The absolute minimum is the very, very lowest point, but since it goes down forever and it goes past our viewing point, again, there's no absolute minimum. So what the relative does is tells us like there is a high point on the graph. There is a high point right about there on my graph. So that is called a relative maximum. So relative maximum, and I would say this is the coordinate, I don't know, maybe like 1/2, 8.5 or something like that. And then likewise, relative minimum is relatively, with the things right around it, it is a low point on the graph. So this, it looks like is, I don't know, about 3, -4 or something like that. But that would be called a relative minimum. And you can just guesstimate on this stuff. There's stuff you can learn in calculus, and that you will learn in calculus for those of you going on with calculus. How to find a relative minimum and relative maximum, super duper easy. Yeah, that's all I'll say about it right now. But for now, you're just approximating, getting kind of close to where our relative minimum maximums are. It's not as easy as finding the vertex like it was in a quadratic. All right, the next thing we're going to talk about is in behaviors. So in behaviors, they kind of go along with each other. And for like x squared, we know if we have x squared, and this is talking about our coefficient. So if the coefficient is positive, it'll open up in both directions. If the coefficient is negative, it will open down in both directions. That's all that means. Notice that exponent is an even number. For a quartic, that's what this is called, Q-U-A-R-T-I-C, a quartic function. It can be doing crazy things in the middle, like it can have little humps in the middle or little curves in the middle, but it's still going to be going the same direction if it is a positive coefficient. It'll be opening up in both directions. If it's negative, take a wild guess, it will be going down in both directions. So as long as we have an even number exponent, right, this was our quadratic. You've seen that one before, we know that one. Quadratic, quartic, the next one, I don't remember what it's called, but it would be like x to the 6th. If it's positive, it's going up in both directions. If it's negative, it's going down in both directions. So the left-hand side and the right-hand side would both be going down. So now, x to the 3rd. We know what x to the 3rd looks like, and if our coefficient is positive, it will stay like our parent function. If it's negative, it will flip it the other direction. So it will look something like that. So if it's x to the 3rd, which is a cubic, we have it going up on the right-hand side, down on the left-hand side. If we have it negative, it does the exact opposite. It goes up on the left, down on the right. Same exact deal for an x to the 5th. Again, it could have weird stuff happening in the middle, but it's still going to be going down in the left, up in the right, up in the left, down in the right, depending on what the coefficient is. And you may need to know this. This is called a quintic function. So if they ask, that's what a quintic function is an x to the 5th. So notice our odd number roots are like our cubic. Our even number exponents, I'm sorry, I didn't mean to say roots. Our even number exponents are like our quadratic. Could be having weird stuff happening in the middle, but essentially the end behavior or the behavior at the ends of the graph will be the same for our parent functions as long as we have like a positive or a negative leading coefficient. Let's see what that looks like. All right, so in example 3 here, that's all we're going to be talking about is the end behavior of the graphs. Sorry. We only care about our highest exponent. So that, remember, that's called our degree. So here, 5 is the highest exponent, so our degree is 5, and our leading coefficient, the coefficient in front of the term with the highest exponent. So the leading coefficient, wow, I cannot spell tonight, come on, would be -1. All we really care about is that that is negative. Since we have an odd and a negative, it just keeps getting worse, an odd and a negative, that means I'm going to be looking something like my cubic, but it will be flipped upside down. So it will be up on the left and down on the right. They may change the wording on you a little bit, but essentially just remember that it's going up on the left and then down on the right. That's all you really need to think about. Let's see, how could they say it? Can't think of anything new to say. I think that's what they use, is up on the left, down on the right. So again, part B, same idea. You're looking at your highest exponent. So I don't even care about the rest of that. I only care about this term. I have an x to the 8th, so it's even. I have a positive 7, so it's even and it is positive. Since it's even and it's positive, I know it's going to look something like a positive quadratic. So that will be up in both directions. All right. Highest exponent, x to the 7th, so I only care about that term. It is odd, and it is positive as well. Look at that, I spelled it right. Yeah. So that means it's going to be doing something like that. It could look crazier than that. I don't really care. All I'm talking about is the end behavior, so I only care about what it's doing at the ends of the graph. So it's down on the left, and it is up on the right. All right. Here, highest exponent, that's all I care about, so I only care about this term. It is an odd number exponent. It is a negative leading coefficient. So that means I'm going to be looking something like that, a cubic, but it's negative. So it'll be up on the left, down on the right. So up on left and down on right. All right, that's really it. That's all I got for you guys right now. We're going to keep exploring more polynomials as you go forward. As always, just let me know what questions I can answer for you guys. I'll talk to y'all soon. Bye.